Hello everybody and welcome to this year's edition of Formnext 2020 Connect. Unfortunately, we cannot be in Frankfurt these days according to the pandemic situation. Therefore, we have decided to invite you all into the Sintratec premises in Burg, Switzerland. For the next 3 days, we have created a fantastic live program which starts every day from 1 a.m. CET, Central European Time. And we are thrilled to have you with us, and we are thrilled to welcome you here in the Sintratec Experience Center. This place, the Sintratec Experience Center, is usually packed with Sintratec customers, packed with Sintratec visitors, so visitors who would like to get hands-on on selective laser sintering technology. And because this is these days not the case, we decided to create an outstanding program for you to bring you as live as possible and as close as possible to the technology as we can. Good, so we will have live print preparation, we will have live laser sintering, we will have live depowdering of Sintratec parts. Every day we have decided to create a specific theme or to work on a specific theme. The theme of this day is rocket science. This means that we will have a fantastic technology talk with our Sintratec customer ARIS. Hello ARIS team. They are basically using selective laser sintered part created on our Sintratec S2 laser sintering systems on rockets, on real rockets. Can you imagine this? And of course, because we are technology enthusiasts as well, a part of our engineering team decided to create the Sintratec rocket science team. This means today we will set up live a selective laser sintered rocket. We will depowder this selective laser sintered rocket. And if you stay tuned until the end of this day, we will launch the selective laser sintered rocket and see if we can reach orbit and if we can reach supersonic today. Right. Good. So this place is usually packed. Today, not with customers, but with a part of the Sintratec marketing and sales team, with Sintratec service engineers. I'm going to introduce you to a few of my colleagues who made this fantastic event possible for you guys. So on the left side here, we have our lovely Vanessa, who is taking care of the Sintratec YouTube chat. So please feel free to answer questions in the chat. If we can, we will answer them, of course. And if not, we will notice down all of them and put them into the chat afterwards. Is that correct, Vanessa?
Exactly.
Good. Thank you. Good. Then on this side, we have our lovely Ramona. Ramona is our marketing manager and basically has created this fantastic, outstanding event for all of you. Ramona, wave your hands. How are you today? All right. Very well. Very well. Good. And I have to be a bit more quiet now because the gentleman here is a member of my sales team. This is Pascal. And Pascal is basically live introducing a Formnext Connect customer who has basically set up an agenda today onto the Sintratec S2 starter cell into this system and technology. Good. So because we cannot be in Frankfurt, we pass our best wishes and greetings to the Formnext family. Yes, we have received the tattoos. Thank you very much for this, and let us create an outstanding and fantastic event together. Good. So let me accompany you then into our 3D printing boardroom, because in this experience center we do not have only parts that we are presenting or simple systems. We have a small part of our Sintratec print service in-house as well, because usually if people or customers are coming by, we do the so-called technology onboarding. This means that customers and visitors have the chance to load the systems, the machines on their own, to get really hands-on on the technology, to see how selective laser sintering works, and to see how we operate with the powder on a daily basis. Good, so let me accompany you. What you see here are Sintratec S2 starter cells. So this print job on a laser sintering station was basically finished this morning. So we did not depack this one. You see the sinter process is done. And this is basically how the surface looks like if a sintering process perfectly has been finished. So you see this small shrinking in the cylinder, and this is basically a finished selective laser sintering project. Good. So this gentleman here is Dario. Dario Arcangeli is one of our service heroes who's taking fantastic care of our customers and is supporting us today in setting up one of the print jobs. Dario, we will be back later with you then. We are first going into the control room and see how we basically set up a 3D print live. Good, so what you see over here is basically our 3D print service plant manager. This is Thomas. Thomas, say hello, wave your hand. Thomas is now setting up, and maybe you can show this live and in action, Janek. Thomas is basically setting up these rockets, these selective laser sintered rockets that we are sintering today. The design have been done by our R&D engineering team, so best wishes and thank you very much for Angelo Bulgaroni and Stefan Noser who created this selective laser sintering rockets. And please again, at the end of the day, we will launch these rockets live. There will be fire, there will be action, and we will see if we can reach supersonic anti-orbit today. Good, then last but not least, of course, in the edge there in the corner, this is our colleague Alessandro from the content generation team. Alessandro, can you wave your hand? So Alessandro is responsible together with my colleague and creative director Janek, who is on the back side of the camera. Maybe you can see him wave his hands today to create this best possible event for you guys. So we really put a lot of efforts in. I hope you appreciate it, and I hope we can give you a thrilling time for the next 3 days. Good, so this is basically the cutting room. And because the pandemic situation happened not that fast, but because Formnext was then cancelled on a personal basis, we decided to give you the best possible personal experience that we can, and maybe take you into this journey of technology onboarding today.
What is happening now in the software?
Basically, what you see over there is, this is our house on software. This is Sintratec Central. Sintratec Central is usually where we are placing the STL files in the software. We place the objects, so you can see Thomas is now placing parts of the rocket and the cover of the rockets or the upper part of the rockets in this system, and later on he's just pushing the button generate print file, and then he exports a PEX file which is basically going into the machine. And this is what we're doing now. So Thomas has finished now the print preparation process. He had put these STL files in. Now he's controlling if there's maybe a mistake. He sees that in the slicing software. Sometimes it can happen that a quality of STL files is broken, or some parts are broken, or triangles are broken. And this is something we would like to avoid before we go into a print job, because this can, of course, cause unusual and unsatisfying effects. Good, so Thomas, thank you very much. Maybe we will come back later on. And now we have seen how a print preparation easily goes. So you place the STL file in Sintratec Central. Again, our house on software that have been built and designed from our software engineers in Sintratec, Switzerland. And now we are going to a Sintratec S2 starter cell. Why are we talking about the starter cell? Basically, we have created this machine, this technology, or not the technology, the system together with our customers. And we carefully listened to them. And a few top feedbacks have been that they would like to have a complete semi-automatic system where they can do the print preparation, where they can do the printing itself, and the semi-automatic powdering to get the best possible starting setup. This is what we call an application enabling system, because if you have one of these S2 starter cells in-house, you can easily scale up according to the production needs and according to your production capability. I hope the sound quality is good. I have to wear a safety protection mask, so please excuse me for that. And Dario, maybe now, again, one of our service heroes, service engineers, who's taking good care of our customers. Hello, so welcome to the audience.
Hello, everybody.
And the majority of the people who have wrote in advance have asked us, about how a print preparation goes, and is it loud, is it dusty, because we operate with powder, we operate with Sintratec polyamide 12, which is an industrial polyamide, an industrial nylon. And Dario is now going to fill exactly the amount into the system that we need to print this rocket for this afternoon's launch. Good. So what you see here just before we start, this is the material handling station, and below we have the material core unit. So these two systems are separated from each other to avoid cross-contamination. You will see later on how we can easily take this one out and put it into a laser sintering station to make sure that the process goes as smooth as possible. Good, so we have been asked as well, is it loud if we operate with powder or not? We have here an 8-zone ventilation system which is sucking the powder on the back of the machine itself, of the material handling station. And in addition, we have an anti-static, is that correct?
Yep.
Vacuum cleaning system that is basically sucking the rest of the powder away, that that the powder is not falling off the system. So Dario, if you would please now demonstrate, I'm going to step a bit back, that you have the best possible audio quality, because it will become a bit loud, but it's not that loud that it's disturbing. Good, so please go ahead.
Maybe show the display, yeah? What's going on there?
Good, so basically what you see here, we have a 4K camera, a 4K system here, where we step by step are guiding the end user or the plant manager through this process of how to do the print preparation. So every single step has to be accepted if you've done it. First of all, to make sure that you followed the entire process carefully, because still it's a high-tech system, it's a fantastic high-tech technology machine, but of course some steps you have to carefully follow to get the best quality out of the selectors laser sintering starter cells. Good. So basically the platforms have been moved down now. So this means the system automatically detects the height and the amount of material you have to fill in to get your part out that you have designed. Is that correct so far, Dario? Good, and then we have these cups, and this is now how Dario is going to fill the Sintratec polyamide 12. Sorry, excuse me. So the print-ready Sintratec polyamide 12 into these two powder chambers before we then actually can start the process. Good, so please. Wie hoch ist denn der Rakete etwa? Wie hoch? Good, so the rocket that we are sintering is going to be approximately 30 centimeters of height, so 300 millimeters. So these powder containers have been moved down very deeply. This is the reason why it takes a bit of time to carefully fill into the material into this material core units as well. Dario, is this a complex process?
It's very easy.
Okay, good. So what do we have to take care of then? I think first of all, the material that we are using is the Sintratec polyamide 12 print-ready powder. So this print-ready powder is a mix of virgin and already used material to make sure that we have, from the economical point of view, the best possible mix ratio for our clients.
How much can you recycle?
Well, the recycling rate or the mix rate or the fresh-up rate is 70%, so 70 already used material, and 30%, so 30% of virgin material, which you are mixing together to get this print-ready powder then. Good, there is one yes?
Will we see the mixing process later on as well, or is that not planned?
I think so. If we have managed to do that today, we will do this as well. Because there is one important point that we would like to hyphenize. After this material is filled into the print container, we have a small coater, so a small tool where we have to easily just put it inside of the powder, because it's very small diameters of powder corn, and we have to make sure that it has a specific density that the powder process, yes. First of all, that it's even, and secondly, that the density is as good to make sure that this print goes smoothly. Good, so you see this now, Dario. What tool is this?
We have to compress the powder with a spatula, just to make sure that the powder doesn't get compressed during production.
All right, so again.
Maybe repeat, because maybe they didn't hear.
Exactly, so Dario is using now a spatula to make sure that the powder is going to be as dense as possible. Is that correct so far?
Yes.
Because this is important part of the process. It's not hard to do that, it's pretty easy actually, isn't it? But it's a small process which you have to take very good care of. Good, and after this is done, he will fill a bit more powder on the top of the edges, is that correct? And then the system will automatically start to create the equal surface, to create the equal surface, and to make sure that this print is smoothly loaded. Correct, Dario?
Yes.
Anything more you would like to mention to the audience, to the viewers?
The only thing you need to take care of here is that the powder bed is covered completely with powder, and the powder is compressed, then you're good to go for your print.
All right, so just in terms if the audio quality was not good enough, we have to make sure that the entire print surface is covered with powder, that the first movement of the coater will create this smooth surface. And what we will do later on, what we can show here as well, Yannick, if you would like to, we have already this finished selective laser sintering print. So this is a material core unit of Sintratec. You can easily add and put more of these systems into your production farm, because you can see this is not a desktop system, this is not a benchtop system, it's a standalone solution where you can easily move this material core unit from one station to the other. So this means if the print preparation was done, because we are using these systems as, well, this is a small amount of the print service that we are having, we will move then the material core unit inside of the laser sintering system. We will start the sinter process live, and afterwards, after the first technology call today, we will be back at about 2:30 to show you a bit about what you can see and control on this fantastic 4K camera screen. Good.
How are we on time, by the way?
Excuse me?
How are we on the time, by the way? So you've got 50 people up there.
I think we're doing pretty good. It's 1:30.
Perfect.
So therefore we are fully on track. Good, so Dario, wait a second. So you can see now the coater is moving and automatically is creating this smooth surface. If there's a bit of material lacking, you can easily just put it above. And if this surface is equal, this means the print is ready to be started. Is that correct, Dario? Good. So on this side we have an overflow, that the rest material that is not being used is going to be down in the overflow as well, because again it's not unusable. You can reuse this material then as well. Good, so Dario, how are we in the timeline?
Yeah, if you add some layers, it'll be okay.
Good. So let me just in the meantime maybe
there's questions, or maybe one question. We saw in the software there was no support structures in the build cylinder. You don't need that, right?
that is correct. So for those people who have not been in touch with selective laser sintering so far, this is a powder-based process. So this means we do not need any kind of supporting structures, like you need them maybe in FDM or SLA technology. This means that the powder basically is holding the parts or the assembled parts or the assemblies inside of the powder cake. We can show you one of these powder cakes if you would like to. So this is basically how a powder cake looks like if the process is finished. This is about 35 centimeter of print, and inside of here there are the parts, the sinter parts or the assemblies, and this is what we are showing you live today, how we depowder then the parts out of this powder cake. Good. You can see again, there's a step-by-step guidance about how to do the process, that you cannot do any mistake basically on the S2 when you're loading the system. And Dario, when did you start it? About 5-6 minutes ago?
Yes.
Okay, so he needed to prepare a print that is basically 30 centimeters of height, approximately with the print preparation that my colleague Thomas did about 15 minutes. And this is usually the average time that we transparently can say, and that our service engineers can even stand that it's a true figure that we are passing here. Yeah? Good, so you see the coater is moving forward and back. Dario, will you bring then later on the system, kannst du Stabsuger?
Can you show us maybe on the touch screen once you're done with the step, how that looks?
Yes, so please, Dario.
We have like a check mark and stuff. Okay, it was the last process, no? Yes.
Good. So this was basically, I hope you can understand me now better than before, I think so. This was basically the time that you need to prepare a print on a Sintratec S2 starter cell system. So again, just briefly before you move it out, Dario, This is the material core unit, totally separated from the material handling station and the laser sintering station. And Dario, would you like to bring the material core unit into the laser sintering station then?
I think we need to help me with the pen.
Yes, that's not a problem. I will help you with the cable because we have had to have this cable that we have the best possible quality online. And you see now how easily it is to create your own production factory, because you can just easily take this material core unit, move it into a laser sintering station. This is a laser sintering station. So here we have the entire sintering technology in, we have the laser in, we have the electronics in, the steering board, and you can see live and in action how this print starts. Good. And now we will start the print job, because we would like to show you live then later on how this print job looks like, how we can monitor it on these systems. And Dario, we are not allowed to touch each other, but please show the audience about how we start a print.
There's little to be done. You need to clean the optics, which is very easy. When you take this glass out by hand. Can you maybe go a bit closer to him so everybody hears him?
Sure. Yeah, so
in this safety distance.
exactly. There's a specific deck you can open up, and it's easy. Basically, you have 2 glasses to clean there. Is that correct, Dario? This is something which has to be done after every printing process or before the printing process starts. So you need to clean these glasses like you clean your usual glasses if you're wearing some, to make sure that the laser is reaching the best possible quality and is not distracted by any kind of particles or something like this. Correct?
Yep.
Good, so please.
So then it's as easy as selecting the print process, selecting the file.
Mm-hmm.
It's the wrong print job in. Select the file, then again you get asked, have you cleaned the glasses? Select this, press start print, and that's it for the beginning, yeah.
Good, so what happens on the screen? What are we monitoring now? So we see the machine warm-up phase is between 30 to 45 minutes, depending on the environmental temperature. You see the height of the print, you see the material we have been using, so Sintratec PA12. It is now calculating the elapsed time for the print. Is there something more we need to mention, Dario?
Yeah, we can see a live view of the print, which obviously at the moment is nothing because we're still heating up. And you can see the temperatures inside the machine. But the main window you need is like the print job window, which shows you what's going on at the moment. Now we are in warm-up for about 40 minutes probably.
Good, and of course we have a live view function, so you can easily just see on the camera what is happening. Dario, would you like to explain?
Yeah, I guess we will show it later when it's printing. Then you can see the laser sintering the part.
To what temperature does PA12 usually warm up?
At around 180 degrees Celsius.
And what's the reason behind that?
It's just to bring it just before the melting temperature, and then we will melt it with the laser.
So to bring the material in the best possible temperature range, that you can easily operate and shoot in with the laser, the delta that we need to sinter each surface. 100 microns is the layer height that we are moving basically. And this is how we can create these fantastic parts that have been melted layer by layer together. Good, so is there anything more you would like to mention from your side as a service hero or service engineer of Sintratec using the systems on a daily basis?
Yeah, so far we have no issues with the machine. Obviously, with service and support, we are more supporting for design aspects, how you can design better parts that are able to be printed obviously in SLS, which you have a freedom of form. So, and just with the product around, you're not having much issues with the machine itself. So
good.
Yeah.
Good, and very important. Thank you very much, Dario, for this. So Dario is one of our service heroes, our service engineers. And for every Sintratec customer, you can justify this, Dario. We usually do a technology onboarding program. And one of our service engineers, Dario, Andreas, or any other, is taking very good care of you, that you can easily dig into this technology, because again, it's a high-tech machine, it's a high-tech system. Some things you must consider and make sure that they have been followed by the manual, step by step, and then you will get these fantastic results that we have. For example, we can see over here, so this is a very complex selective laser sintered assembly. This is a dinosaur, which we call Big Al. Big L, Thomas, how many parts does Big L contain?
4 parts.
But the dinosaur, how many parts are it?
Sintered out of 4 parts, huh?
So it's just sintered out of 4 parts. So this entire dinosaur was sintered in one Sintratec S2 print cake.
You have a video of that online, by the way.
Yes, we have a fantastic video of that online as well, where we link the sources and all of the professors who supported in creating this fantastic stuff. We have a local Swiss company called Econauten.ch, which has basically did this illustrational support to transfer this complex object into the selective laser sintering data, into the files that we can print it. And yeah, show it, maybe not live, but show it at least the way this dinosaur looked like thousands of years ago.
You mentioned the small size, right? With laser spot size.
Exactly.
So you can pretty much see that at the rib cage here. Very good.
Exactly. So what else do we have here in the Sintratec Experience Center? Maybe just briefly. We do not only have the Sintratec starter cells, of course. So give you a brief glance at the history of Sintratec and how we started. The first machine that was developed by Dominic, who is today our CEO and co-founder of Sintratec, Christian, who is the CTO, that will later on talk in a technology explanation talk program to you guys, and Mr. Joscha Zeltner. So these 3 people created this fantastic and outstanding selective laser sintering kit. So this machine is really the world's first and still only selective laser sintering assembly kit. So it comes for the price of approximately 5,000 euros. And because it's an assembly kit, so people with a technical background like I have, you really enjoy 3 to 5 days of building this machine, and then you get the full deep know-how and knowledge about how selective laser sintering works. So it's an easy to handle machine. It has just 28 kilograms of weight, and it stands in more than 200 plus universities all over the world, where university students or research scientists are doing basically development of new materials for the additive industry.
Why is it so great in research then?
I think because I will show you one specific example. It's a low price, low cost solution that makes it possible for everyone who has a limited amount of budget to dig into this technology and to use and manipulate it. Maybe if you would like to operate with materials that have been not existing, like from our colleague Fabrizio that I will show you. And if something... The parameters on the Sintratec kit are open, that is correct. And basically, the advantage is if something breaks or happens in this system, you just lose a system of 5,000 euros. So let me bring you to this example here. This is a customer use case we have as well on our website. This is the customer use case from FaberX, which is basically a spin-off of the UCL in London. So you will see the interview, a live video. So Fabrizio and his team, the team from Professor Simon Gaisford, hello Simon, if you see us today, basically did something that we didn't thought about. They have sintered medical tablets out of a specific material that is basically white or yellowish, and found the right parameters to create and sinter then these medical tablets. And this was, of course, a fantastic program. And this was done on Sintratec kit systems. So first with one and afterwards with multiple ones that they are using in their operational lab.
All right. Any other use cases do we have time for?
Well, we have multiple use cases you can find on our website, on our YouTube channel. We have a fantastic industrial use case of Geberit, Switzerland. So Geberit basically is using our systems for industrial prototyping to make sure that the prototyping process can go fast, and especially that they can reduce the time to market and solve on-site issues fastly. Maybe they are at the end of the day not using our technology, they use maybe a mass production technology, but the process to create these prototypes as fast as possible, like this isolation shell is working fantastically and good. And this is an industrial use case which is basically showing you about the power of selective laser sintering and this technology. Yeah. Then we have Fabrizio and his team with the medical tablets. We have one of our favorite industrial designers, Stefan Henrich, who will on day 2, I think, talk about compliant mechanisms. So it will be a fantastic talk about what compliant mechanisms are. So Stefan is really one of the pioneers in selective laser sintering industrial design. He's teaching at 7 different kinds of universities or educational schools. I'm sorry if it's not 100% correct, but you can see these fantastic designs. So even this bike was sintered on a Sintratec S2, and we hope that one day we will see thousands or millions of them on the road because the design is astonishing, and he's really one of the pioneers doing that. And of course we have here the team from Subsea, so maybe fitting to the topic of today, to ARIS and our rocket science theme, because what Professor Alberto Ortona is doing, basically he's creating these gyroid structures with our systems, where he's putting a high temperature ceramic paste over it, burns it out in an oven, and can reach fantastic different kind of attitudes on the material as well, and is changing basically the possibility where to use and how to use these objects. Yeah.
We have a question.
Yes, please.
He asks, how much powder do you have to add to the machine for this print?
Who was asking this question, please?
This is Mark Ireland from Australia.
Mark Island, okay. Hello, Mark. We've already been in contact. I still owe you an answer, I know that. But with Formnext, we just didn't manage to do this round. So basically, the print is 36 centimeters of height. So the exact amount we have to fill into the powder range, I can later on put into the chat at the end of the day, because I do not know it off the top of my head. But again, the system is automatically detecting the depth about how much material you need to put into this system. Good. So we will answer this question in the chat then. Good. So then we have a few examples we can show. You know, COVID-related items, unfortunately, have been very needed these days. We have fantastic thermoplastic elastomer materials. So maybe, Vanessa, can you catch this one? Catch this one. Good. Very good. We have, so whenever someone is asking us about how big can you print on the S2, I think the main question is how big can you think on the S2? Because this one here, this is not a design from us, but we have printed it just out for showcases. This is a sword, and you can see it's constructed out of multiple parts, and it has been sintered on the Sintratec S2. So if you go now away from this sword construction and think about maybe something like an industrial tool where you can easily detach construction, then this is a fantastic tooling component as well.
I just got a quick feedback.
Sure.
Could you repeat the questions, Gabor? When Jan or me asked you the question, could you repeat it? Because they said they won't hear us.
Absolutely. Okay, good. So the question from Mr. Mark Island from Australia. Good day, Mark. I hope you're all well down under. Was how much powder did we fill into this system to create this selective laser sintering rocket? And again, I do not know it off the top of my head, but we will write it down in the chat later on that you have these measures when I cleaned it or asked my production plant engineer then. Okay? Good. So basically, maybe one important thing about the S2 as well. We still have a few minutes of time. So the print cylinder is not rectangular. It's circular. It's circular, and this is the height of a selective laser sintering print that you can print in a Sintratec S2 system. So the print cylinder is 400 centimeters. The optimum print height is 360 millimeters. The diameter is approximately 135 millimeters. And you see usually this is what comes out then of the system itself. And this is a typical print where you can fit multiple dozens, hundreds or thousands of small mid-sized parts. And yeah, this is how the print container looks like, yeah.
So it can fit a lot of parts in there, small parts.
Yes, it depends, of course, on how big your parts are. So you have small parts like this ones. You can imagine that you can feed hundreds of these parts inside of the system. So we just put in a petrol-colored paper to make sure that you see everything. So you can imagine how many of these parts to fit into this print cylinder. I think it will be more than 100. So for industrial production, for industrial additive manufacturing, it's the perfect system, it's the perfect starter cell, from our opinion and from the opinion of our dear Sintratec customers, to dig into the technology and do this onboarding program. Yeah. Good, so Janek, you just basically put your attention on these things. This is going to be a technology talk on the third day of the event with one of our dear engineers, Stefan Noser. Here we will talk about surfaces, and this means we talk about different surfaces that you can use for different kind of applications. You see, Stefan has invested a lot of time to make sure that in this talk, I hope you will attend, you must attend to learn this, about how easy you can transform different kind of surface structures onto this polyamidic surfaces, yes. Good, so I think, Janek, do you have any question left?
Maybe in the chat?
Yes, please.
But repeat it. So they hear.
Sure.
There's a question from Andres. He asks, how long does it take to heat the laser sintering system, and also how long to cool down until you can take out the cylinder?
Okay, fantastic question. Andres, is this the gentleman from Mexico, maybe? So hello, it's great to have you with us today as well, Andres. Lovely. So I hope, or maybe you didn't understood it when the process was running, but the question from Andres was, how long does the system need to heat up the material and to bring it into the perfect temperature that the laser sintering process starts? So this process takes about 30 to 45 minutes, depending on the environmental temperature. And you see this is a fast process where we easily heat up the system then to bring it on the top of the temperature level. And I think to give you the best possible formula, because many people are asking us how fast is the laser sintering, and it always depends on many factors. So first of all, how many parts do you have in the print cylinder in? Because the best possible formula we can give you without knowing the parts, your parts or the size of the parts, is basically that one layer that is 100 microns of height needs about 5 to 45 seconds of sintering time, depending on the amount of parts. So if you have a big part like this one, maybe I can demonstrate this one. Janek, if it's okay for you, then you have more or less 20 or 25 seconds. And if you have, of course, multiple small parts which are filling the entire print range, then it comes more or less to 45 seconds per layer. But this should be approximately the maximum time that the layer needs. So 45 seconds to create this prints layer by layer, 100 microns going up. Good. I hope, Andres, I was able to answer your question. So by any means, stay tuned until the end of this day, because this rocket launch we are doing will happen today, and we are astonished as well to see about how stable selective laser sintering parts can be sintered, and if we reach supersonic and then the orbit hopefully as well. Yes?
Helder says, should not the cake be in a container much larger? After all, there is all of powder which can easily fall apart.
Good. Can you please repeat the question for me?
Actually, he asks if the container where the cake is in it,
Okay.
it should be much larger, so
Good.
that no powder falls.
Good. What's the name of the person?
It's Helder.
Helder. So Helder, thank you very much for asking this question. So what you will see this afternoon as well. So in 45 minutes, we will have a live view on the sintering system started to sinter. And later on, approximately 1 hour later, we will do the depowdering process of the powder cake. And this Helder may answer your question, because usually, if the powder cake is finished, it moves up in the material handling station system. So it looks exactly like this one, well, more or less exactly like this one. And then you put it like this. And because the depowdering process, the semi-automatic depowdering process, takes part in the material handling station, where we have these ventilation systems and the vacuum cleaning system, you have a minimum amount of powder that is basically leaving the machine or is on the edges of the system as well. We will show this live, Helder, so please stay tuned or tune in again for this session that is going to take part at, I think, 3:30.
Yeah.
Something like this. Good. So I think if there are no more questions left in the chat, we have more questions in the chat. That's lovely. Okay, we have an interaction with our clients, with the audience.
There's another question from Arturo. Is there a cooling time in a 30-hour production that has just started?
The question, the name was?
It's from Arturo.
Arturo. So Arturo, welcome and thank you very much for joining in. So there is a cooldown time, of course, in the system that the polyamide can get the best possible quality. So this means we have an automatic cooldown system in the laser sintering station first, so excuse me, in this station, so when the material core unit is in here. And after a specific amount of time, this depends on the height of the print. You can release the material core unit, move it besides, so I will demonstrate this for you. So more or less, Arturo, it looks like this. So the print is done. Oh, Janek, let us go to the other laser sintering station where we have the print, take care of the cables. Good, so Arturo, this print is finished. The system shows you the blue color that it's okay and cooled down. And after an amount of time, depending on the height of the print, this can be 1 hour, this can be 5-6 hours. You can detach or disconnect the material core unit from the material handling or from the laser sintering station. You can take this core out, move it besides to cool down. And then you can already easily, so I hope you appreciate the action I'm doing, Arturo. Huh? Good, so you can already easily refill then your next print job into the laser sintering station. So this is how it works. It's basically a fantastic, easy to use design. As you can see here now, the print job is heating up. So I can see about how the temperatures looks like. We are on a surface temperature of 169, and these are a few measures where we are giving. And yeah, I think at 2:30 we are going to be back and show you live about how the laser sintering process looks like. Important, you have a live view in here, so you can scale this one up and move it with your finger to see what happens. Now nothing happens, because first of all the material is going to be brought into this perfect temperature range before the sintering process starts. Good. Vanessa, any more questions?
No, there are no more questions.
Good. So this was the first introduction. I was very happy to introduce you to my team, where we are in the Sintratec Experience Center. At 2 p.m., so in 4 minutes, we will have our CTO and co-founder of the company, Mr. Christian von Burg. He's going to hold a presentation about deep dive technology insights of selective laser sintering. Very interesting. Christian is going to explain to you why we not use white materials, why we use dark materials, and many more things that have been asked or questions that have been raised in advance. So enjoy the next 30 minutes, and we will be back live here in the Sintratec Experience Center at 2:30. Thank you very much for your time, and see you later, guys. Bye-bye.
Good. Hello and welcome to this Sintratec Tech Talk about lasers. First, I would like to give a little bit of context. So, who are we? We are Sintratec and we build laser sintering equipment. So this is in additive manufacturing, 3D printing. So if you run an in-house prototyping service or if you have small series production, you definitely should have a look at our products. But first, I would like to introduce myself. I'm Christian. I'm CTO and co-founder of Sintratec, and I'm excited to talk about lasers in the next about 30 minutes because I get asked about these quite a lot. And this usually goes like this. So our customers are used to seeing white polymer SLS parts because the industry has been printing white parts for quite a long time now. And Sintratec prints in black or dark parts. And this sometimes leads to confusion, and I get asked a lot about this. And people ask, well, why is this? And I say, because of the lasers. And they ask, is it because the laser needs more power? And I say, not really. But I can explain. Do you have 30 minutes? And usually people don't have 30 minutes. But today I was given 30 minutes, so I'm very happy to talk about why we are printing in black parts and not white parts. Let's jump in with some laser physics. So I keep it simple, but we need some basics. So the process of laser sintering, I'm going not too deeply into this because that would be another tech talk, but basically we shoot a laser at some polymer powders and we melt one layer, and we do this over and over again. So we get, in the end, we stack all these layers to a 3D printed polymer part. This is selective laser sintering, and as I said, I'm not going too deeply into this. What I want to talk about today is the laser and the laser beam itself. So we steer a small laser point across a powder cross-section, and wherever the laser hits, the powder melts, and we can form a 3D object. This is important because with this we can print pretty much every object without having a tool for it. So we don't need a mold or anything like that. We can just use the laser and steer it across the powder bed. Now we do this with 2 motors and 2 mirrors. You can see them up here. We have one motor for the x-axis and one for the y-axis, and with this we can steer the laser across the powder bed. We do this very quickly, and we have a focus lens to focus the beam onto the powder to have a very small laser spot and to melt the powder. Now, talking about the laser beam itself, I would like to talk about the light. So what's different about laser light than compared to normal light? If you have on the very left here, normal light coming from instance, from a lamp, this is so-called incoherent light. So you have all the colors mixed and they're going in all kinds of different directions, and your eye actually looks at all the colors and decides, okay, this looks white to me. So white light is mixed light with all the colors. In a laser, you have one very distinct color going in synchronous in one direction. That's kind of the difference, and it's much better to work with this for this application because it's better to have optical components manufactured just to one coherent light. When I say color, what do I mean by color of light? It's actually an electromagnetic wave, and the color is determined by the wavelength. So I plotted here 3 waves, a blue one, a green one, and a red one. And as you can see, the blue one is the shortest one, and the red one is the longest one. Down here, you can see the whole entire visible light spectrum, so our eyes can see from blue to red, and that's about it. And these are shorter waves and these are longer waves. Now, why is this important in laser sintering? Why do we care about the color at all? So basically it's because of the interaction with objects. I have this example for you. So if we have incoming white light that is shining onto a green apple, what actually happens there, the green apple, the material of the apple acts like a mirror for green wave length. So the green light is reflected from the apple, and your eye up here is perceiving the apple as green because the green light is reflected. The blue and red portion of the light is absorbed by the apple. So it gets stuck in the apple and the apple gets a little bit warm because of it. So the apple absorbs these wavelengths as heat. And that's how your eyes are actually able to see the apple as green. Now, if we want to cut the apple with a laser, we can use a very powerful green laser beam and try to cut the apple. But actually what happens is almost all of the energy of this light is reflected by the apple and nothing happens. So if we want to use a laser to cut this apple, we need, for instance, red light, because all of the red portion of the light is absorbed in heat, and voila, we are able to cut the apple. So that's the trick about it. And even though the red laser has exactly the same energy as the green before. One special case is black. So if we have a dark or black material, all the visible light wavelengths are absorbed, and our eyes don't receive any light from the object, so we see it as black. And so basically what this means, if we use black powder or black objects, we can use pretty much every laser pointer in the visible wavelengths that exists, and we can cut this object. Now the opposite are bright or white objects. These act kind of like a mirror for the whole visible light. So if visible light or white light is incoming onto a white object, everything is reflected, nothing is absorbed, and we see the object as being white. A very simple example of this is actually a car. So you might recognize this if you put a white car close to a black car into the sunlight. After a while, you notice the black car will get much hotter than the white car, and this is exactly because of this effect. Now, how can we cut white objects then? For this, I have to expand your view a little bit into the electromagnetic spectrum. So basically, if you go from short blue waves even shorter, you end up in X-rays and gamma rays, so that's the same, but you cannot see it by eye. And if you go from red waves even longer, you go first into infrared, microwaves, radio waves. It's also the same, but also these waves you cannot see by eye. Now, I want to extend our 3 waves with 2 new ones. One is the near infrared. So this is just a little bit longer than the red wave. And we have the far infrared, which is much longer, like 10 times longer. And I have chosen these 2 because of the absorption of polymers. Now, I've plotted here the absorption spectrum of polymers. And as you can see, if here in this direction there is an elevation, we see that polymers are absorbing the light in this region. So we have absorption in the UV spectrum, but we don't have good lasers there, so we don't really care about this region. Then in visible light, there is no absorption. In short infrared, there is no absorption, but I included it because we have very, very good lasers there. So some of the best lasers you can buy for money are produced here. And then we have the long infrared spectrum, and here polymers absorb naturally. So you don't have to have a color different one, they absorb it. And this is why these two are included now. And including these, the example would look the following. So we have all the waves coming in, the short ones, including the short infrared spectrum, are reflected, and the only one being absorbed from white parts is the long infrared one, the really long ones. And this tells us, okay, so if we want to work with a white polymer powder, we basically need a laser that works in this long infrared spectrum. And having such long waves has other inputs as well. So not to go too deeply into this, but basically the shorter a wave, the easier it is to have a really small focus spot. You can see the mathematical formula here. And if you have a very short wave, it's much easier to have a small focus point. If you have a really long wave, you get a larger focus point. Now, why would you want to have a small focus point? It's like drawing with a pen or with a brush. With a pen, it's much better to have a smaller resolution, sharper details, and also sharper edges. So your part quality will generally improve if you have a smaller laser spot. One thing that I want to include, and this would be a whole another topic, but depending on what material you're using to build your lasers and how the laser is built, there are different shapes of laser spots. We start with the single mode, so you have more or less one point of light that has one intensity maximum, and from there are several multi-modes, so moving up the ladder, depending on the material you use, you don't have one point but several, and this can or cannot be a problem for your application. Now that we have the basics, I want to have a look at 3 products in the industry. So one of it is stands here for the general industry standard, I would say. The picture is of an EOS machine. And before we, Sintratec, started, basically every machine was using these CO2 gas lasers in the very far infrared spectrum that I was talking about, so you would be able to print bright or white parts. When we started, we first built the Sintratec kit. It's a desktop machine, and it uses very short blue laser light. I will talk about why, but the middle product that is displayed here is our Sintratec S2, and it uses a near-infrared laser. So in this, it is already invisible, but still quite short wavelengths. Now there are several advantages and disadvantages on top of the color. So one is footprint. If you have a diode laser, these are very small. So I have described it here as a credit card footprint. So you can more or less build a desktop class product like we did very easily. The fiber lasers are the size of about a shoebox. And then we have the CO2 lasers, and these are long glass tubes. They start at the size of about a skateboard, but they can be much longer, and they are bulky, and you would never be able to build such a small product as the Sintratec kit with such a large CO2 laser. Then I want to talk about the absorption. I think I made this pretty clear in the first part. So those two diode lasers and fiber lasers, they need absorbers, so the part need to be black, and the CO2 lasers with the far infrared, they are operating in a region where the polymers absorb it naturally, so we can work with bright powders as well. Then, moving on to the focus spot, basically the diode lasers are multi-mode, so they have not one but several spots. So this, your part will suffer a bit from this, but also they are have a short wave, so you can focus it down very good. So this makes up for the multi-mode in some way. But the best laser by far is the fiber laser with a single mode, short wave, so you can focus it down really nicely, have a perfect spot. CO2 lasers are single mode as well, but because of the 10 times longer waves, it's much harder to focus them in a teeny tiny spot. I think one of the most important topics about the laser is lifetime. So I plotted here the lifetime of these products, and I researched a corresponding animal. So how long does a ferret live? Now I know it's about 10 years. And this is the same about the diode lasers and fiber lasers. They have lifetimes up to 10 years or even more, while the CO2 lasers, they only have about 1 year of lifetime. So if you have a product that you need to replace your most expensive component, the laser, every other year, it's quite expensive. But if it lives 10 years, that's no issue. So lifetime is a big topic. So in conclusion, we have these 3 areas of focus. And I would say it's fair to assume that no laser can excel in all 3 of them. So not one of them is just the best in every category. So what we focused at is beam quality and cost of ownership. So the increased lifetime, the small footprint, and the exceptional beam quality just make the fiber laser stand out to us. And I want to talk about the material color. So what are we losing actually here? And people or customers sometimes ask, do we suffer from material diversity? And because not every powder or every polymer is available in black as well. Now, this is quite easy. So what you can do, or what the industry does, is add additives, and usually it's done with carbon black. That's a very inexpensive and good absorber. So a lot of materials can be dry blended with just a little bit of absorber additive. I've described it at 0.5%, and the material will not suffer from this small amount of absorbers, and then it's printable with our printer. Now, with post-processing is another region that needs focus on. So there are several different post-processing methods, and I have plotted some of them here. And we have all of these, I would call them coating post-processing methods. So whenever a small coat of something is applied to the product, then it doesn't matter if the parts are white or black. So the only difference is if you scratch the coating after, the part beneath would be black or white, but that's the only difference. So for all the coatings, there is absolutely no difference in post-processing whether you have black or white parts. Then one big area is dyeing. So if you want to dye the part itself, then there is a difference. If you have dark parts, only dark colors are available. And if you have white parts, you can do pretty much every color. The last thing is if you want to have them untreated. So if you want to have the natural part untreated, uncolored, then of course the one is black, the one is white. But there is one important thing. For instance, our customers from automotive really enjoy this. So here, with the UV stability, black parts are naturally much more UV stable. So if you put them into the sun, they will stay black for a very long time. And the white parts will start to degrade, get a little bit yellow. This is because of the sun and oxygen. So this is an advantage of black parts. So as you can see, it really depends on your application, on what lasers and what parts are desired. And for us, it's really no questions. We are going for the very nice fiber lasers and the black parts. And I hope this presentation was able to show you why our parts are black. And I'm very happy to answer any of your questions.
I would like to buy the Sintratec S2, but I really would like to print with white powder. Is it possible to build in a CO2 laser into the S2?
So the question was if I want to buy a Sintratec product and I really want to print in white powder, is it possible to include it in our system, so to build it? And I would say definitely, but it depends on batch size. So if you order enough of these machines, we will build everything for you. For one machine today, no.
Thank you.
Welcome.
You said that there's additives in the material. Does this mean only the black material has additives, or do the other materials also have additives in them, the white ones?
So these 3D printing polymers are always a mix of base polymers and lots of additives. So the white powders have additives in them as well, but different ones. They also are improving performance with the CO2 lasers I mentioned, but they are white to the eye, so you don't notice them as much as the black additives that we put in.
Could you color the powder also like dark blue or green and use it in a fiber laser machine? So the question was if we could color it a different color, the powder, so not black but maybe green or something like this. And this would be possible if this specific absorber has absorption in this fiber laser range. Absolutely, yes.
When you print with a fiber laser and when you compare it to the CO2 laser, the end product, the part, is there a difference between the different lasers for how strong the part is in the end?
So if you use, the question was about strengths of the parts. Do they differ from white to black parts and the lasers? And in general, I would say no. So if you use the same polymer, there are slight differences, but basically the small amount of black additive that we put in makes no difference. So they are the same in strength, but if you look at different machines and different parameter sets, there still is a difference, but I would say a small one.
So you said there's a fiber laser and there's CO2 lasers. So are there any advantages in the final part with the fiber laser?
Yes, the question was about the part itself and not the strength or the color, but more or less the shape of the part, if there's a difference. And definitely there is. So as I mentioned in this presentation, the fiber laser can be focused down to a smaller, nicer spot. And because of this, smaller details, better resolution, and also sharper edges are possible with the fiber laser.
Why have you decided to build a small system instead of just one very big?
So we have decided to build a small system, which was the question, and not one very big one, because we see a lot of advantages in having redundancy and scalability. So basically, if you have a lot of medium-sized or small systems, you are able to scale your in-house prototyping or small series or large series production. You can start small by having one system, then move on having 2, 3, 4, and not bind a lot of capital at first. But also you have redundancy in printing. So if you want to start one print in the morning, you can do that. And if there is another one coming on noon, you can print then. And if you have one large machine, you always have to wait until you have enough prints to fill the whole system. Or if some parts might fail during print, it's much better to have, or if your system fails, I mean it's broken, and you have 10 systems, then you have still 90% of your production capability. If you have one large system and it breaks, you have 0%. So that's much better for redundancy. Yes?
Can I develop my own material on this machine?
Absolutely. So we have an upcoming product with the open parameters. So you will be able to access every parameter of the machine and develop your own materials. For this you have, for instance, to have a variance in laser power or laser speed, and you can choose your own parameters for your material. Absolutely. Good. Thank you.
Könnt ihr das? Tanzen so nicht? Yeah! Hello everybody, we are back in the Sintratec Experience Center in our premises in Burg, Switzerland. We already had the first session about how to do the print preparation of an STL file on our Sintratec S2 starter cells. We have had many questions from the audience. Thank you very much for joining us and for asking those. One question we still owe an answer. This was the question from Mark Island in Australia. So hello to Down Under. I think it's approximately 1 a.m. local time. I know that because I was living and working in Brisbane, Australia many years ago. So thank you very much. Your time is appreciated, Mark. So the feedback from the technical engineers was that each of these print containers holds 6 liters of Sintratec polyamide 12 to print this 25, 28 centimeters of height rocket. So if you have any questions left, do not hesitate to call me after the event. Good, so what we would like to do now is we basically have set up the print itself. The print, we told you that the heat up time of the system is 30 to 45 minutes. And we are now going to the S2 and have a look about how it looks like. So I'm going to be supported by my dear colleague and service engineer, or I call it service hero, Dario. And yeah, let me accompany you and let's go live onto the printing system. Good, so Dario is back again because he thought in the meantime, maybe if there's interest given, we will show you about how our mixing process takes place, about how we sieve and mix in a laser sintering station. But first of all, Janek, if you can come closer, you see that the print is basically has been started, excuse me, and it needs approximately 22 hours of printing and cool down time. Then, Dario, is that correct? So the time is estimated, it's a mathematical calculation, it's more or less good, and you see a few temperature zones that are stated here, Dario. So we have the actual temperature of the top surface, is that correct? So it's between 187, 183 degrees. We have the build cylinder, which has 200 degrees of temperature, the preheat zone and the doom zone. So do you know what these ones are, Dario? The last two?
Yeah. So the preheat zone is where the reservoir platforms are. Where the powder gets preheated before it gets coated onto the build area. Mm-hmm. And the dome is like the area above in here, where underneath the laser glasses, which we showed before. And yeah, we have just like the whole system everywhere where we have powder or contact with powder is temperature controls with heaters and sensors.
Okay, good. So I hope you've been all able to understand what Dario said. So you see the system is now colored in green. So this means it's now actively and live printing. So what we did an hour ago is we have prepared this print job together with our plant manager of the 3D printing service, Thomas, and now we have a look about how this looks like. We have a 4K camera system inside here that detects actually and shows you in the best possible quality the top surface level of the layer. So Dario, would you like please to support me or assist me in choosing the view? So we have the print job, the live view, and the temperatures range. And now you can see exactly what happens in the system. So the coater has been moved now from the left to the right side, put on material on the layer, and you see how fast, this is real time, how fast this surface, this layer has been sintered.
Can we get a bit closer?
Yeah, sure, get a bit closer now, because you see how fast our power laser, our 10-watt power laser is basically operating.
We heard about what the laser actually is in the talk, right? So
Exactly.
It's a fiber laser.
It's a 10-watt fiber laser, that is correct. And you see, this is really live. So this is not speed up or slow down. This is the live print process story. Is that correct? Yes. So every time 100 microns of Sintratec polyamide wafer are going to be put up. The heat zone heats up the top surface layer. The IR sensor detects the temperature, and then the laser starts to operate. And you see, this is really, really, really fastly going. And I think one of the top major points where this difference is, we have a galvo laser, a galvo steered laser. And if you compare it with other maybe desktop or benchtop systems, it's 3, 4, 5 times faster because they have mechanical movements in the laser head. We have decided to use a galvo laser, so this was the decision of our R&D team. To make sure that we have one single laser source that is basically shooting out in all edges, and that we can fastly or speed up the laser sintering process. Good, so Dario, we see the percentage and the amount of time that the print already has been done. So this takes now about 22 hours, and of course, because we didn't want to take your entire time, we already pre-printed this powder cake yesterday. So this powder cake is ready, and we are going to depowder this one live at 3:30, I think. Good, so ladies and gentlemen, this is all I can say now, because the print process, for the ones who see it the first time, they usually enjoy it with a bowl of popcorn and watch it. But it's basically sintering or melting, sintering layer per layer together to complex shapes or parts or assemblies with freedom of form. This is it. Is there anything more you would like to tell the audience? Like, so what else for is this camera needed, this 4K system? I mean, we can steer, we can swap between the print job, we can see the time left, we can see the height of the print, what print was printed or is actually printing. We can see the temperature ranges. So this is the entire magic, or not the entire magic, but this is part of the magic. So you do the print preparation, you bring this material core unit to the system, you make sure the surface is smooth. The machine detects automatically the chosen file, the STL data. Sorry, the PEX file, which was created of the STL data. So you can have a library of parts you can choose from. And then actually 30 to 45 minutes of heat up time, the process starts. And yeah, then you have to cool it, the machine down, and then you can take out the part itself. Yeah, this is it.
Let me just maybe show the camera again?
Sure.
So for those people who haven't seen it yet.
Can also zoom in a bit.
Oh, yeah.
So it's a 4K camera. It's really high quality in terms of the resolution you can enjoy. In the history from the first systems we started from the Sintratec kit and the S1, we had a orangish or an orange laser protection glass in order that you can look inside of the system, but of course you could not see everything because of the angles and all these things. So this was one of the main feedbacks of our customers. Can we have something like a 4K camera system where we see how the print goes, how the print is doing? Yeah, so and, Dario, maybe anything from your side as a service hero or engineer. I mean, what else can you see on the screen? That's just the entire process. Huh?
Yeah, obviously we have, if customers have problem with their prints, we can see in the live view what's going wrong. Maybe you see some issues with the part or how the part are placed in the powder. But that's the main advantage of having a camera instead of just looking through a window into the machine.
Yeah.
Additionally, the machine is logging every layer, so then the customer can send us or has cloud access, and we can see the log file. Might see some errors in there to support the customer. Yeah.
Good. So what are typically, from your experience, the the field issues that customers are having if they have an issue with the system. You know, is it the mixing ratio? Is it maybe that some waste came into the powder, which can happen? You know, we had this case once or twice where the powder was cross-contaminated with one, like a piece of metal or something in it. What are the typical, you know, from your experience, cases that customers should be aware of? Yeah.
Definitely, contamination of powder is one thing that the customer needs to take care of, and we had issues with this when they made something wrong in the mixing process, which is actually guided very clearly on screen when you do it. We'll show it later maybe. Then it's like how you place the parts inside the volume in the Central 2 software. So you have like a long part which gets interrupted by other big parts. So you have other layer times and different sources of heat that could affect the long part, stuff like this. So there we support with design ideas or show them how to place the parts inside the Central 2 software.
Mm.
Yep.
Good, so thank you. I think there's my colleague Pascal again. Pascal, just can you wave your hand? Oh, he's live pitching, excuse me. He has basically a Formnext Connect, hello Pascal, person of interest, yeah, where he's presenting the system.
Maybe you
Good.
can say something about Formnext Connect for people who are watching us there.
Yeah, I think the Formnext Connect was a fantastic initiative from the Formnext steering committee. I mean, when it was clear that the event cannot happen physically, they have set up in not no time, but in a very limited amount of time, this fantastic event platform where you can virtually connect with each other. But I think for us it was important to do besides, or give the audience the chance to see how we usually operate on a daily business in this experience center. And I think, yeah, this is a good win-win situation for both sides. We have the platform to connect, where I'm later on having a customer chat as well. I'm looking forward to it. To do that, and yeah, to bring you a bit more close as personal as possible, you know, to show you about what we are doing here and how it looks like, yeah. So I think one thing we could do as well, because we still have a bit of time left. Just 1 second. Vanessa, any questions? Vanessa, questions?
Yes.
Please.
There's another question from Arturo. He's asking if after the printing, should the cooling process occur in the sintering machine?
Okay, so the question from Arturo, hello again Arturo, thank you very much for joining in for the second time, was does the powder cake needs to be in the system for the cool down process? Is that correct?
Yes, and he's also adding, or can we just remove it and put the second build unit inside to make new prints during the finished build unit gets cooled?
Good. Arturo, that is 100% correct. So the print needs to stay from a specific amount in the laser sintering system to do the first cool down, that the material is not going to have a thermal shock, how we call it, that you get the best quality out of the system. After a specific amount of time, this depends on the height of the print. The system can be detached and the material core unit can put besides. And yes, you are correct. If you have already prepared the second print job, you can move this material core unit inside of the laser sintering system. Again, you have to clean in this desk the glasses. So there's the IR sensor glass and the laser protection glass. And if this is done, you can already restart again. That is fully correct. So if you have your production capabilities in-house and if you need to scale up, you can easily do this. It's working like a revolver is the wrong word, you know, I don't want to use this term, but it's working basically like an semi-automatic solution you can automatically fill in. But important, and this is something we still have time, which we can show, is how about the sieving and the mixing process, because one of the biggest advantages of this system that we did not mention so far is, so let me accompany you, is that basically these three Swiss-made, it's Swiss-made quality, Swiss-made engineering quality, that these three Swiss-made systems have multiple advantages. One very important advantage is that, if you come closer, that in the material handling station, we can automatically sieve the material that was not used but put into the print, Dario. This machine does automatically, so this material co-unit automatically sieves the used powder. You will have a bit of waste left. This takes about 40 minutes to do so. This waste you can put into the rubbish or take care of your social, economic regulations or ecologic regulations to put it there. And then you fill in here the used sieved material. In the middle you fill in the virgin material, and the system automatically is mixing then the new print-ready powder for you. So if you would like to, we can demonstrate it. So is there interest from the audience?
Do we have time for it?
Yeah, I think we have another 12 minutes. Okay, so I think then Dario is going to help me. So we're showing you another important process, the sieving process in the material core unit. Because Arturo, this should answer your question. If you have a material handling station where you do the print preparation for the second print, you can do it in the material handling station and afterwards put it automatically into the system. Good. Showtime. Thank you.
Maybe you can.
Yes, so basically you see on our steering window, it shows you really step by step what you have to do. So we are here in creating print powder. This is the print powder process. 70% of used material has to go into the print container. And if you agree, then you start the process, Dario. Then you have to check if this material core unit is empty, of course, that you have no cross-contamination. You have to wear protection masks and gloves. So Dario is just getting his gloves because you see this is an easy to do process as well. The software tells you step by step what you have to do. Good. So I'm going to move besides. I'm staying a bit closer because of the microphone. Don't worry, we are COVID-19 protected, at least what the officials say with the protection masks. Good. Then it tells you that you have to take care that the orange material, so the used powder, these print containers are labeled. Exactly. Orange means used material. Good. Next step. Now the powder beds are leveraging, they are going down, and important is then that here on this side, is it okay, Dario? We have this special industrial sieve, where we have a small engine on this sieve, which is shaking basically the sieve to make sure that the material comes down and is sieved. Good. So you can easily attach this sieve. Then you can fill in the polyamide 12 powder, the used one. Dario? Dario? Good. Sure. So I'm assisting you today, yeah? Very good. Pleasure. It's hands-on training for the head of marketing and sales as well. Basically, in the meantime, as you can see this process, I did it personally as head of marketing and sales for 8 weeks when COVID started. So we changed the shifts and produced 24/7 some medical devices. We produced door handles, which we gratefully got shared with Materialize to make sure that everyone has them fastly. A few medical applications where we are not allowed to talk about. And we have a fantastic COVID-19 use case of our dear customer Materia in Italy. It's on our website. On our website, check out the tab Customer Use Cases or Customer Stories, and you will find all the industrial use cases from Daimler, Materia, Morad, and other of our fantastic clients that you can see how it works. Yeah.
Question.
Yes.
When you say you don't have like the background, like you're not an industrial support engineer, it's still easily for you to operate, even as a layman, so to say.
Yes, I have a technical background personally, but when I started to operate these systems, when COVID-19 started, my colleague and dear CTO Christian von Burg online basically gave me a 2-hour training about how to operate the Sintratec S2 starter cell. And within no time, really no time, I was able to do this. So I operated these systems about 8-9 weeks, 7, 8, 9 weeks, not sure any longer. I had 3 breakdowns, and all of these breakdowns on the system have been my fault. So therefore, Christian, if you see this, sorry for that, but your training was great. And you see that with this starter cell, it's easy to remotely learn it as well, because this is part of the technology onboarding program that our customer service engineers like Dario are basically giving to the audience. Good. So you see a bit of powder is coming there. Shall I attach the vacuum? Good. So if you now zoom over here, you see that the already used powder, so the rest of a print, is not waste, but you need to sieve it to make sure that small particles, maybe like these ones, are coming off, that they are not blocking the process.
We have a question?
Yeah, you have 2 more questions.
Yes, please.
I think now is a good time.
Do you produce yourself the Sintratec materials, or are they outsourced?
So the question was if we produce our own Sintratec PA12. So basically, we have a source of industrial giants who are delivering polyamides to all different kinds of industries. So the basic material is, of course, not from us, but we have an additive in the material that is absorbing our laser wavelength beta. Therefore, it's branded as Sintratec PA12 and Sintratec TPE material. I think this is by far the best answer I can give, because please, we many times have the question, and this is a correct question, of course, from a customer who wants to have an open system. If you would like to operate third-party materials, it's possible to do that, but please be aware, our material established industrial 3D printing production quality. So our R&D engineers, our software engineers invested thousands of hours to find the right parameters to get the quality that you receive. And if you decide to go for a different material, it's not impossible to do that, but please be aware that we cannot take any guarantee, because there are hundreds of thousands of materials on the market. And one of my customers even used once Sintratec PA12 branded from Alibaba.com for, I think, $10 US, and the result was, of course, a mess, because it came from an uncontrolled source. And to make sure that industrial grade quality comes, you need 7 process steps to qualify this material before it goes into our systems. Good, so I hope I answered this question so far.
Yeah, there are 2 more questions.
Yes, 2 more questions just before I answer those. You can see that Dario will use now again the spatula, because the material is not fluid, of course, but it's very, very, swimmy, you see. So we have to make sure that we compress it a bit, we dense it a bit, again. And here is the used material in, and now we will put in this cylinder, where we usually have the prints, the PA12, the Sintratec PA12 virgin powder.
So that's your fresh powder from...
Exactly, this is labeled, so you see we have these economic containers. This is blue labeled. Then we can open up this one. Is it okay if I assist you, Dario?
Yep.
Good. Any more questions, Vanessa?
Yes. Is it possible to dye the materials, even if the laser capability is only to a certain of color? And do you provide a system to do that, or is it dye by you?
Good. So one of the questions was, is the material dyeable? Is that correct? So basically, I'm going to bring you an example. Excuse me. Just 1 second. So again, I repeat, the question was, is the material dyeable? And we are not the experts in doing this for the process, but what we can show you is that if you have a look at this part, so we have a bunch of sample parts here. This is originally out of the machine, and this is basically post-processed. So because the material is dark, it's actually, let's say it, easy to dye it into dark color ranges. Bright color ranges is difficult, and we are not the experts on this. We already have our experience, but this is not something that we can support at this stage. Maybe, not saying that much, or having said that, in the near future.
Can you show the other one again?
Good.
The dyed one?
Yes, just briefly about how it looks like. The coloring is totally different, but industrial grade coloring, this is not our expertise. Good, so maybe Dario, again, here is the used powder. Here is the virgin powder, how we call it. So this is the orange color is the used powder. The blue color is the virgin powder. And now, please. Yes?
So we are adjusting the platforms to be on the top surface. Beforehand, the machine automatically moved to the correct position, so you have the correct 30% virgin, 70% used powder mixing ratio, so you don't need to care about this. In the end, you just need to have them on the same height, and then we can start the mixing process.
Good, so both platforms have been moved up now. You see they have to be equal as well. So this is totally at 100% live. Huh? So what you here see is one of the top advantages of the S2 starter cell system, that the not used material can be sieved, mixed, and made ready for print-ready material in this one system. So this is really a fantastic advantage where we are very proud of, that we have created the system like this. So a big compliment to the R&D team and to our construction engineers, because this was one of the top feedbacks from Sintratec clients who have been using Sintratec kits or Sintratec S1 systems in the past. Good.
All right. Now the sieving and the mixing starts.
So you see this engine on the sieve has started to shake, and now the coater is putting this material, the used and the virgin one, over the sieve, and this industrial graded sieve is now shaking, and what stays left on the top of the surface is the waste, and the rest which falls down into the container is the print ready material again. Good. Dario, anything more you would like to mention to the audience?
No, it's just like this is the important part, that you do not mix up different grades of powders, so you will have a perfect printing powder, and then there should be no issue with your prints.
Good, so maybe if you zoom on, Janek again, so it will move one layer again into the sieving station. So you see it puts it goes over there, it's automatically, the engine is shaking, the sieve is letting the polyamide down that can be reused, the rest stays as a bit of waste, so these small cones over there. So this is the entire waste you have, almost nothing. Good, so I think having said that, we go back to the sintering machine, Dario. Okay, any questions, Vanessa?
To dry the PA12 before printing?
So the question from whom?
It's from Peter Schäuble.
It's from Peter Schäuble. Do we have to dry the polyamide before printing? Dario?
No, actually, with our heat-up cycle we do. It will be dried during the print heat-up in the laser sintering station.
Exactly. So please just take care that the bowls with material are closed, that no humidity comes in, and basically the rest, this system works like an oven, so it's heating up, and therefore it's going to be dry when the print process starts again. Yes? Any other questions, Vanessa?
Yes, and why does it take so many hours to cool down? Does it have to cool down slowly and in a room temperature, or can it process faster by cooling artificially?
Good, so the question from Helder was, why does it take so long to cool the material down? Basically, Helder, your question is correct. So the material, the first cool down stage happens inside of the laser sintering system. Then you open up the material core unit and put the system besides to cool it down outside of the system. Because we heated up the entire print cylinder into a specific temperature, it has to take a specific amount of time not to damage or to warp, not to create warping or curling maybe. So different words are in the field now. that the part really gets the best quality. If you do this too fast, you will get warping results. And if you do this too fast, maybe you can change the density of the parts as well. They will more easily break. And this is a process where we figured out this is the best for us working. I think there will be multiple industrial programs to do this with additional cooling of air and all these sort of things. But they all, as far as I know, failed because it just needs the specific amount of time that you get the best industrial grade quality out. Good.
There's one last question.
Sure.
How versatile are the parameters in the S2 that you can use to fine-tune third-party powder materials?
Excuse me, can you repeat the question?
Of course. How versatile are the parameters in the S2 that you can use to fine-tune third-party powder materials?
Okay, good. So the question from?
It's a question from IME2.
The question from IME2 was how versatile are the parameters in the laser sintering system or in the S2 starter cell to do research or science on different kinds of materials or use third-party materials. Good, so basically the Sintratec S2 system for industrial grade users is the closed system. Of course, I don't have a name, so IMO2, you can have specific software where you have a range of open parameters to adjust and to use third-party materials. Therefore, we have to take a monthly or annual fee. And then you have these parameter settings to operate or use third-party materials or do research on your own, yes. Good, I think we are a bit... I think we are a bit over time. Ladies and gentlemen, I hope the second session was as interesting as the first one of the day. So, we covered, firstly, the print preparation. Secondly, Dario, thank you, wave your hands. We covered the sieving and the mixing to do the print preparation. And we will be back in, I think, half an hour, more or less half an hour, to show you live how we are depowdering a powder cake in the Sintratec material handling station. And we will get our industrial selective laser sintered rockets out of the Sintratec starter cells to make sure that we can do a fantastic launch today, try to reach supersonic and try to reach the orbit. And let's stay tuned, it's going to be interesting. Right now, so what's up next is a fantastic technology talk with one of our Sintratec customers. It's the ARIS space program. And the ARIS space program had basically received selective laser sinter parts out of the Sintratec S2 systems, and they are using them on real rockets. Again, they are using them on real rockets. So stay tuned and enjoy this technology talk between our creative director, Jana Kuschke, and our customer from ARIS. Yeah, and see you later. See you in a few minutes. Bye-bye.
Sorry guys, we had a technical difficulty here. We will, of course, restart the talk we pre-recorded. Sorry about that. Yeah, I will just restart the pre-recorded talk I had with Michael Kerschbaum about ARIS. So stay tuned. Sorry about that. Hello everybody and welcome to another Sintratec talk. Today we're shooting for the stars and talking about rocket science. I'm very happy to be joined by Michael Kerschbaum of ARIS. Hello Michael.
Hello Yannick.
Michael, can you give us a short introduction about yourself and ARIS, for people who don't know what that is?
Yes, so as already introduced, my name is Michael Kerschbaum. I'm the system engineer of ARIS this year, rocket project Euler. And what ARIS does is basically we're building rockets, but not only rockets, we're also building rocket motors and anything that's associated with aerospace. And we do this in the frame of a student organization. Every year we collect about 80 students from all around the German-speaking part of Switzerland and engage them in building rockets and rocket motors.
Very interesting. So ARIS stands for Akademische Raumfahrtsinitiative Schweiz, which means Academic Space Initiative of Switzerland, you can say. What is the general vision behind it? What would you say?
So I think we at ARIS are pushing for more aerospace topics in Swiss universities. I think with the great engineering minds of Swiss students, this topic is still underrepresented in Swiss universities. And in this way, we understand ourselves as a force pushing forward aerospace topics in the field of academia in Switzerland.
Mm-hmm. So you said students you are collecting basically from a variety of universities. What's your background? And you're working in a team called Project Euler. What's the background of your team there?
Yeah, so I'm a physics student, but we're not limited to only science students. Our team is very, very diverse. So we have students from different fields of studies such as physics, mechanical engineering, electrical engineering, chemistry, and even management, for example. And in this way, we kind of get the best of every field of study, and everyone can bring in the knowledge they already acquired during the studies and build up on that and get some hands-on experience, like designing real rockets.
So
tell us more about Project Euler, your technical leader of. What was your team working on, and how did it go so far?
So every year in ARIS, there's a rocket project, which is there for building a rocket to compete at the Spaceport America Cup. This is a competition where student teams from all around the world come together in the desert of New Mexico to launch rockets and compete against each other. And Project Euler is the rocket project of ARIS for the years 2019, 2020. And our goal was to build the first supersonic rocket of ARIS, and indeed the first supersonic rocket of any student team in Switzerland.
Interesting. So how did the year turn out? I guess COVID-19 did sabotage that as well to some extent, like most project in this year, or how did it affect you?
Yes, so unfortunately also Corona didn't stop for our project. We had to cancel our maiden launch, which was planned in spring, and eventually also the Spaceport America Cup 2020 was cancelled due to COVID. And this was a big impact for the team, or this had a big impact on the team, because this was kind of the main goal everyone was working towards for 1 year. And now this goal being gone, we needed to reevaluate our mission goals and what we wanted to achieve for our project.
Mm-hmm. So what are the next steps? Do you continue with that project, or where is that leading now?
So for us, we had a launch back in summer in Switzerland. Actually, the first launch that was organized by the student teams. We, together with the team from EPFL, organized this maiden launch in Switzerland. And after that, we are still planning for launching our rocket supersonic. In Switzerland, of course, there's too little space to launch rockets to the full height. So we are still looking into possibilities of launching our rocket supersonic.
Mm-hmm. Can you, maybe for me, who has absolutely no idea about rocket science, can you tell me about like the differences between, you said it's the first rocket to actually go for supersonic. So what's different in regard to previous student projects, and what are the challenges basically for that?
So yes, so the first supersonic rocket also means that the rocket will be subject to greater forces than previously known. I mean, you know that when you're going by car, and the faster you go and you hold out your hand, the stronger the force on the rocket. And there are some aspects of the rocket that need to be engineered in a particular way. For example, the rocket's fins, they need to be designed in such a way to really withstand the forces during supersonic flight.
Yeah. Okay. So how optimistic do you see the project going? Do you think you will be able to achieve that goal that you set yourself and for Euler?
So for us, we now finished our second rocket. Based on the learnings we got from the maiden launch, we built the second rocket, and we are now looking into possibilities of launching this rocket. And this is actually quite a hard task, because in Europe, such projects are not very well established as they are in America, for example. Yeah. So we really have to look and see whether we find an appropriate place to launch our rocket.
Yeah. Interesting. So let's switch the topic a bit to 3D printing, because Sintratec was actually involved a bit in that project. We sponsored certain parts for your team's rocket. And so in general, did you use additive technologies in constructing your rocket? Was that part of the of your construction process?
Yes, so indeed we use additive parts throughout our rocket, from different parts such as the launch lugs, which hold the rocket in place while during liftoff, to structures for mounting board computers. For us, it's a very convenient way of fast prototyping, and also a cheap way to mount lightweight structures inside the rocket.
Mm-hmm. So can you maybe give us a summary of what types of 3D printing technologies you were using, and maybe why?
Yes, so mainly we used FDM, which we printed ourselves for, as I already mentioned, for purposes of mounting board computers inside the rocket, but also, for example, for guiding the motor inside the rocket. So very different points of use there. And also we used SLS, which we got sponsored from Sintratec as our main part to guide the rocket off the launch rail. And this is a very, very crucial part because it really determines the flight of the rocket. If the launch lug doesn't hold in the first few moments of the flight, the rocket cannot go off the launch rail safely.
What were the requirements, the material requirements then for such crucial parts?
So for us, there is one main requirement, which is also a requirement from the competition itself, which is that whatever structure we use, this structure for the launch lug has to hold the rocket in place, and it has to support the full weight of the rocket. And in this way, we had to do a bit of prototyping ourselves with our in-house 3D printers, but in the end came to the conclusion that we needed something more robust than that.
Yeah. So was that the reason why you took SLS, selective laser sintering, into play there instead of, I don't know, other printing technologies?
Exactly. So there's basically, or let's say the standard approach for these parts of the rocket is to get aluminum parts and turn them. The problem with that is, however, that this strongly limits the opportunity of optimizing the aerodynamic shape of these parts. I mean, these parts are mounted outside the rocket, meaning that they have a big effect on the drag of the rocket, which then again limits the performance and how high the rocket can go. So in this sense, it's good to have the possibility to aerodynamically optimize the shape of this part, but at the same time, you want to have the robustness that the rocket is really kept in place during liftoff.
So you had a launch, as you said, in summer. So did these launch lugs that we laser sintered for you, were they a success, you would say? Did they hold what you expected?
So for us, they worked perfectly fine. I mean, the launch lugs weren't tested during liftoff the first time. This would have been not safe for us. We did some prior testing, of course, for that. But even during heavy testing, we couldn't destroy these launch lugs, which meant that we deemed them safe for flight.
All right, that's good to hear, of course, that that all worked. So what would you say in your field, what's the biggest advantage that you gain from constructing these parts, not only those laser sintered parts, but I mean in general the additive manufactured parts in your prototyping process? What would you say is the main advantages you gain from constructing it and building it in that way?
So at least for our project, I mean, we're a student project and we do not have the possibilities of having access to, I don't know, drilling or turning machines. And in this sense, using additive materials offers a big variety of using it inside the rocket. And it also allows us to, for example, very quickly integrate new features to our rocket. For example, we decided shortly before the launch, meaning a month before the launch, to include further board computers to measure additional aspects of the rocket during the flight. And this can only be done if you have access to technologies such as SLS or other 3D printing methods.
What would you say are the disadvantages?
I mean, while the SLS parts are certainly very robust, and for our use case of guiding the rocket off the launch rail, they work perfectly fine. I think right now we are still not there, or we do not have the materials yet to use them in very heavily mechanically used parts, like, for example, the parts that holds the motor in place. So in this sense, we would not use the SLS parts or other 3D printed parts in such mechanically strongly, parts that are heavily mechanically used.
But would you say in general in your field of aerospace, do you see these technologies having a place in developing rockets?
Yes, so for us, it's, as I already mentioned, they offer big flexibility when prototyping, of course, but even beyond that, when trying to integrate new features to a product that you already, for example, fully designed. Having the access to additive materials really allows one to be very creative with integrating new solutions and coming up with new ideas that would not be possible otherwise.
Yeah. So you already mentioned the example with the board computers. Do you have another example maybe of like a success that only came into play with 3D printing technologies? For example, something, I don't know, that you perhaps constructed in a different way before and then switched it to additive manufacturing and it turned out to be the better choice?
Maybe not in that direction, but in a similar direction. So we had to, shortly before our launch, change the motor that we used because of issues with importing the right motor to Europe. And this meant that all of a sudden the parts that we built for holding the motor in place, not mechanically, but just to guide the rocket, they were not proper anymore. And we had to quickly come up with a solution for that. And the way we did it was to 3D print these parts, and it worked perfectly fine.
Interesting. I think this COVID crisis, to us at least, showed a bit how the importance of local production. So we had other student projects that we sponsored parts to, and it kind of revealed that it is important to rely on local partners instead of, like, I don't know, international deliveries that may be cheaper, but in such uncertain times may not be very reliable. So was that an important factor to your, when constructing this rocket? Did that play a role in your project?
Yes, so you should probably not get me started on issues we had with manufacturers from outside Switzerland. There have been huge delays. Also, due to Corona, we waited for some parts from the US for 3 months even. So having the opportunity to order parts in Switzerland, basically a few minutes of car ride away, and in the worst case, just go there and pick them up, was now in hindsight, very valuable. And we probably, or at least I will recommend the next teams to use make use of as much Swiss companies for manufacturing rocket parts as possible.
Good to hear. So apart from Euler, ARIS has a variety of different projects, right? So can you maybe talk a bit more about other projects that you know make use of additive technologies as well and how they are used there? Do you have maybe some examples?
Yes. So as I already mentioned, this year, beside the rocket project Euler, there's also the project IRIDE, which is working on their own motor, a hybrid rocket engine. Mm-hmm. And one part of such a engine, rocket engine, is the nozzle. So the lower part where the rocket exhaust is coming out. Yeah. And in fact, it was considered to make use of additive technologies even at such a crucial point, because it allows a cheap way to manufacture such complicated shapes. Of course, there again, there's the problem with what material you use, because they are subject to very high temperatures. But even then, the team did not give up on this idea and is further investigating the opportunity or the possibility of using additive materials for their motor.
Yeah, I think it's a big research topic as well. We have a customer use case about the research in the southern part of Switzerland, Subsea. They are, for example, using our machinery to 3D print like gyroid structures that they want to use for like ceramics that can be used for exactly that topic. Can you maybe talk a bit about, for you, like if you could like dream of an ideal scenario where 3D printing is part of that aerospace field, what material requirements would be like a game changer in your eyes?
Yeah, so I think for us, as already mentioned, in aerospace in particular, drag is a very big factor. Mm-hmm. So being able to arbitrarily change the shape of parts that are subject to either the drag from the airflow around the rocket, or also from the exhaust of a rocket through the nozzle, being able to produce any shape one or the simulation guys can think of, is very, very important. However, to really make use of this technology in aerospace, in the places that I just mentioned, one probably needs to work on materials or find materials that can, on the one hand, sustain the forces acting on them during rocket liftoff and during supersonic flight, but also, as you already mentioned, high temperatures, for example, when using it for structures close to the motor exhaust.
Yeah. Do you see personally in that field, do you see technologies like ours, selective laser sintering, being part of that industry, as it may be for prototyping or as end-use parts like you used it?
Definitely. So for us, as I already mentioned, it was not only the prototyping aspect, because we used your parts really as parts that were flown in the rocket. But I can also think of use cases where one easily and very cheaply can try very different shapes and test them for mechanical properties. So for example, one could still try to optimize the part that you were so kind to make for us, and do this in a way that one could not do when using other techniques of manufacturing.
Mm-hmm. So maybe a bit of final words about ARIS. Where do you see that project going in the future? Will we see like a big Swiss aerospace program at some point, or what is like, where do you think that is going to go in the near future, let's say?
Yeah, so for us, it's one of the main goals is still to continue building rockets and to be one of the first student teams to reach orbit even. But not only on the technical side, we are trying to push the boundaries in Switzerland, but also, as I already mentioned, on the academic front. We really want to push for topics of aerospace in the curricula of universities in the German-speaking part. And we see our role to promote universities to have their students engage in projects such as ARIS, to have them ready for future use as an engineer in some aerospace company.
Yeah, absolutely. I think that's the key, right? To be like right at the source. I mean, we from Sintratec are trying that as well. We have a lot of research institutes that already make use of our technology in the education. So maybe your personal conclusion and summary of the cooperation with Sintratec. How was it for you, and how happy were you with that cooperation with us? And yeah, maybe where do you see us working potentially together again in the future?
Yes, at this point, I definitely also want to thank you at Sintratec for supporting our project. We really count on as I already mentioned, the Swiss excellence in engineering. And for us, working together with you was always very unproblematic. You were very responsive, had the parts manufactured immediately. We didn't really feel like being sponsored or being treated as different. We really felt as if you were pushing for us as you would be pushing for any other partner. And we will definitely hope to be able to continue working together with you. So we really want to make use of your know-how and the knowledge you have in producing such parts, because as we already saw, there's many ways of making use of them when building rockets or rocket motors.
So maybe someday we will see some Sintrat parts in orbit from the Swiss space program. I would look forward to that. We will, of course, have a use case about your application in the near future to read more about this. But I think for now that was a great preview of what's to come. And yeah, thank you very much, Michael, for your time and talking to us about this interesting field. I think it was very insightful. And yeah, I'll leave the last words to you.
Yeah, thank you, Yannick. As I already mentioned, there's a lot of people working hard to have this rocket come together. First and foremost, of course, also our academic partners of ETH, HSLU and ZETA AW, and also our main sponsors, Burg and Maxon. Together with these Swiss companies, we were able to build the first supersonic rocket of Switzerland and also the first hybrid rocket engine. Thank you.
All right, and thank you everybody for listening. We will of course continue with our Formnext Connect program, so stay tuned for more interesting things to come. And yeah, thank you everybody for tuning in.
Good. Hello, everybody. I hope that you're back again from this third live session. So what we are doing afterwards, or what we will do now, what we promised you to do today is we did the print preparation, we did the live sintering, and now we are going to do live depowdering of Sintratec PA12 polyamide parts. This means the rocket design that we have put into the machine, into the system to getting sintered, we are now depowdering live, again with the help of our fantastic service hero, Dario Arcangeli. Good, so let me accompany you again. So here you see the rocket is still sintering. Everything is on track. This was where we stopped an hour ago, and I really hope that you enjoyed the ARIS technology talk of our dear Sintratec customer with the space program. Good, and let us go over here. Dario, hello, we are live again. So Dario is basically live depowdering the parts now in the material handling station. So what you see is that the powder cake has been finished and sintered. And Dario, maybe you can soak away with the vacuum a bit more of the powder. And you see this is live. This is no fake. This is live how the Sintratec rocket is coming out of the Sintratec powder cake. So you see after the print has been cooled down, it has been cooled down perfectly. It's basically very easy to release. It's basically very easy to release the rest material, the not used material from the parts or the assemblies itself. Good. Ich mal schnell absaugen. Okay, so you see here the design of one of our rocket, or one of our R&D members who's part of the Sintratec rocket science team. You see that Dario is soaking away the not used material, which goes into this container, which is marked yellow, or orange, excuse me, which Sintratec used PA12 in it. Good, so Dario, can you please explain a few things? I will translate it for the audience because you will hear the vacuum cleaner in the back, and it's not very noisy, but with the microphones that we are having, these high quality microphones, yeah, it looks like this. So this is really live depowdering on the Sintratec material handling station. And again, the Sintratec S2 is a starter cell, a laser sintering station, a material core unit, and a material handling station. So best in class price system all over the world. You will not find any better semi-automatic laser sintering basic system setup, which is a perfect application enabler that you can easily scale up according to your production needs. Good, so we have a few tools over here. We have a brush, we have an additional remover, and yeah, you can see the quality, may I? Quality looks very good. So this is the Sintratec rocket, yeah, and Dario is basically now depowdering these parts straight out of the machine, yeah. Good, so.
Maybe you can go to Vanessa and answer some questions while we are...
Yes, we have a question. Vanessa, please.
Yeah, of course. RM protective eyes were recommended when handling the powder when dusting the part off. No eye irritation.
Okay, so there was a question. If we do not have to wear protective glasses, Dario, do we have to wear protective glasses?
No, the air extraction system is actually strong enough, so there is not really powder coming my way.
All right, so the correct answer is that we have these 8 ventilation zone systems that are sucking the powder away. With the additional vacuum cleaning solution, there basically is no powder coming into the eyes. Is that correct? And of course, it's live, it's not speed up, it's not slow down, so you see really how we usually do it. Of course, we do it a bit slower, that all of our viewers have the chance to see about how this process goes on basically. In the meantime, yes?
Okay, about the vacuum cleaning solution maybe? Can you something say about that?
Well, I can only say that it's an anti-static vacuum cleaning system, which is soaking the powder into the Sintratec PA12 fused powder. And here you see what we started an hour ago or 45 minutes ago. Here is basically again the sieving process taking place. This was a question from Arturo from the last session that we have had. Can you use two systems besides? Of course you can. We have one material station, we have a second one. Here we do the depowdering, and here we do the print preparation of the parts. Print preparation of the powder, of course, yes. Good, so Dario, how's it going?
All fine. Moving easily.
Good, you see the ventilation system is sucking the powder away. So what do you think, how long will it take to clean this part approximately, Dario?
Probably 5 minutes for the print job. If you have a lot of small parts, it takes longer. If you have big parts, maybe repeat what you...
Good, so cleaning this Sintratec old selective laser sintered rocket takes us about 5 to 15 minutes maximum. We can do it faster, of course, but we decided to slow down the process for you. So yeah, thank you very much, Dario. We will be back in a few seconds because it's always the same thing, depowdering live on the material handling station. There was a question which I maybe would like to answer about how many parts fit into an S2 system. So Janek, if you come with me. Still, the laser sintering process is still going on. So this is exactly the same rocket that we are depowdering now. You see again, the coater puts material on it. The laser is basically sintering layer by layer together to complex parts of freedom of form. Good. So I have prepared something for you. Yes, Vanessa, is there a question? Please, Vanessa.
When depowdering, is there a problem if you suck into the vacuum any sintered powder? I mean solid polyamide sintered parts bigger than the powder particles.
Who was asking this question?
It was from Andres.
From Andres, good. Andres, thank you very much for this question given. So basically, no, because we have an additional setup that you can put on the vacuum. If you know that you have small parts, very small parts, you can put this filter on the vacuum. And I will show it to you. Yeah, we can show this live. Dario, may I? So basically, this is our own created filter attachment. You can see this one. This is from Sintratec. I think our R&D team, Mr. Stefan Noser and Angelo, designed this part.
And it's simple.
It's very simple. You can, many of these parts on the system we are sintering with our own machines. Dario, we will be back. Can you show maybe please the rocket again?
Getting there.
Awesome, getting there. So yeah, please continue. And in the meantime, let me do, this is now a real life demonstration. So nothing made up. Janek, is this okay? Good. So let me go. Hi, Ramona. So this is a demonstrational S2 system which we're usually using to send it all over the world. So this is the S2 print cylinder, and I was asked about how many parts have place in this print cylinder, which is 360 millimeters of height and about approximately 130 millimeters in diameter, okay? Are you on focus, Janek?
I can get a bit closer.
Yes? Would you like to come from this side? Okay, good. So that's okay. How many parts do fit in one of these print cylinders? Are you on focus?
Let's see it.
Good, let's see it. So small parts, how many fit in? So if this is not a huge amount of parts that is coming out of this Sintratec PA12 cylinder, I do not know what you define with industrial additive manufacturing, but these are all parts that have basically can be put into one of these Sintratec S2 starter cell systems.
Let's go back to the rocket again.
I think so, yeah, let's go back to Dario. So I showed you the amount of parts that usually fit into one print cylinder. There are multiple ones. Is there any questions from the audience? Good, so let's go back to my colleague Dario. Dario, how's it going?
Fine, yeah. Cleaning out the inside.
Good, so first Dario removed the rough amount of powder. Now he's going a bit more into detail, so take care. If you have very thin walls, if you create selective laser sinter part with very thin walls, that even in the cleaning process you take good care that you do it smoothly, okay? If you have robust parts, it's not a problem, then you can easily just shave like this. But we wanted exactly to show you that this wall thickness is about 0.3, 0.5 millimeters only. So it's very, very thin. How much is the wall thickness there?
I think 0.6 or 0.5.
Good, we can show this to you live. So this is an industrial measuring tool. Dario is a qualified service engineer who knows how to handle these tools.
Down here is 0.8.
Okay, 0.79, 0.8 is the wall thickness of this selective laser sintered rocket. And again, after we depowdered it, we're going and we launch it into the orbit. So stay tuned, yeah. Good. Any questions? Good, so ladies and gentlemen, feel free to ask questions if you have some still left, because the depowdering process is going to take another, I think, 3 to 5 minutes. In the meantime, I think for those who didn't have the time to enjoy this complex dinosaur called Al that we have sintered in one Sintratec S2 print cylinder, I mean, that's a fantastic example. Of course, for such thin constructions, you have to very carefully remove the powder of them, but you can see it's not a problem. You can do it if you take care of the machine and the systems itself. Good. Maybe there, in the meantime, there was a question as well about how stable or how industrially can we use Sintratec PA12. And I would like to raise your attention. We were having a very good video on our YouTube channel from a turbine that our industrial engineer, Andreas Kuster, hello Andreas, designed, and the rotation was with about 30,000 RPM, so 30,000 rounds per minute. And this is a video that you can see live on our YouTube channel as well. You see, this is not a fake, this is a real engine we let running, and yeah, it's fantastic to see about how strong and reliable these parts are. Good. So, again, before we go back to Dario, a Sintratec starter cell is made out of 3 high-tech machines. The laser sintering station, a material core unit, and the material handling station. This is, from my perspective, one of the best industrial printing or 3D printing SLS solutions on the market. Price range approximately $40,000 US to start with. And then you can easily extend and scale up your production. Goed, Dario? Wat je wel afstellen?
Ja.
De wou ik gewoon mal abstellen. Good, so we are almost finished. We are almost done with depowdering our rocket. Dario, can you please show it?
Yeah.
So we have a top head of the rocket. We have a lower part of the rocket. And I think, yeah, from our perspective, this was... Yes, Vanessa, we have a question, please.
Yes. IMD2 asks, if you print a hollow part, is it advised to have air holes open to let the powder get out, or is it more beneficial to leave the powder inside a hollow part?
Okay, so IMD2, thank you very much for your question. The question was, if you print a hollow part, does it make sense to leave a few holes to take the powder out of the part itself, or shall you just close the shell and leave the powder inside? Well, this depends, of course, on the application and your applicational need, because if you create small holes where the powder can come out, of course your part will be lighter. If you enclose the shell, then the material, so the powder stays inside of the part, of course, and there it's going to be more heavy. So this is it. You can then even sinter the surfaces together, or you can leave the powder inside and enclosed. This is possible, but again, please be aware that the weight of your part is increasing, and if you have the chance to do that, release the powder with some small extraction holes, and then you will have a fantastic quality part, which has a very light weight, which is these days very, very requested from different kinds of industries. Good. Vanessa, do we have any more questions? Not now. Ramona? Good. So I think we will have another 2 or 3 minutes until we are done. So we will do this now. We will finalize this. And I think, Janek, is there a question from your side still?
Maybe you can show us again, like the sintering process that is still going on this machine here?
Sure, absolutely. So for those who didn't have the chance to join our first or second live session where we did the print preparation on our Sintratec Central software and with the material handling station, Again, here on this system, the print is live taking place. So this form, this shape, this surface that you see is basically exactly the same rocket that my colleague Dario is screening now and depowdering in the material handling station.
So you can work parallel, you can clean in one unit and sinter parallel in the other, right?
Sure, of course. I mean, you must imagine if you have 5, 6 of these Sintratec starter cells, you can easily extend with additional material core units, material handling stations, according to your production needs. Then mostly 2 or 3 people are operating the systems, or maybe 1 plant manager is operating the systems. And if you use this economical circle, this semi-automatic solution of the S2, then you always have a circle in production, preparation, depowdering, where you at the end of the day can take your parts out after a short time. Yeah. Good. May I? Darf ich die schnell nehmen? Good. So for all who have been still with us, this is our selective laser sintered rocket. This design was done by our colleagues from our rocket science team, Angelo Bulgaroni and Stefan Loser. Thank you very much for that. I'm now, or afterwards, going to grab my jacket, and we are going to see the launch of this rocket then outside of our Sintratec premises in Burg. Basically, what's the rest of the program, Janek, today?
We will see it in action, hopefully, and then you show us back here again for just maybe showcase what's up in store tomorrow.
Good, so thank you very much for your attention and your time till now. We will be back in a few minutes. First of all, I'm going to grab my jacket and I go outside, and then we will launch the rocket, and hopefully we will see if we can reach supersonic or even the orbit. Good.
Let's go.
Hello everybody, we are here outside of the Sintratec premises in Burg, Switzerland. Today we have already learned about how our dear Sintratec customer ARIS is using selective laser sintering technology to create parts for rockets. Of course, we wanted to try this out ourselves, and with the help of our Sintratec technical rocket science team, we are now attempting the launch of the first Sintratec space program. And of course, we are very excited to see if we can reach supersonic today. Well, let me accompany you to the launch site. We are here seeing now the Sintratec rocket, which was sintered on the Sintratec S2 system. I have my dear colleague and lead technical engineer Stefan Loser with me. So Stefan, would you like to phrase a few words to the audience about what do you think the stability of the rocket is, and if you think we can reach orbit today.
So I think the weather conditions are well and we are ready to boost. Looking forward to it. And about supersonic, almost, I guess.
All right, so thank you very much, Stefan. We are very excited. So let's get the launch started. The countdown is running.
Are we ready? Okay, set your lighter.
Where's the lighter? I think we are ready for the test now. Take off in a few seconds. 3, 2, 1, go! Hey! Go! Woo! All right. I think, thank you very much for the team. We have successfully completed this first Sintratec space launch program. It was very exciting for us to see about how this demonstration was going on. And so far we have completed our first Sintratec special outdoor event. I'm giving back to my colleagues in the Sintratec Experience Center. Good, so I'm back again. I hope you enjoyed the launch. It was freezingly cold outside. It's already November. So the exactly, good. So I'm back again. All right, so ladies and gentlemen, for all of the viewers who tuned in today, for the entire audience, in the name of the entire Sintratec team, I would like to address a big thank you to you, that you have spent a bit of your time, and we really appreciate that you have tuned in. I mean, we had a fantastic program, hopefully created for you today. I would like to put special thanks to the entire Sintratec team. So Alessandro, where you can't see him, he's in the corner there. Dario, wave your hand, who supported us today. Then our lovely Vanessa, who has taken care of the chat. Ramona, our marketing manager. And we really, really hope that you enjoyed this first Formnext Connect 2020 live event in our Sintratec premises in Burg, Switzerland. And please make sure that you tune in tomorrow again, because at 1 a.m. CET, so Central European Time, we will start the second day of our live program. We will have, again, live presentations. We will have fantastic technology talks. We will have one of the leading industrial SLS designers, Mr. Stefan Henrich, talking with me about compliant mechanisms. For those who do not know what compliant mechanisms is, tune in. It's going to be a fantastic event. And we will have a customer of us, eTech City, I think it is, where they are giving us deep insights about how they are using selective laser sintering technology to create the e-bikes of the future and to make sure that e-mobility finally is going to be spread in the cities all over the world. From Vanessa, that we have one more question. Yes, please.
Exactly. One more question from Helder. Do you have to physically clean with an instrument, or can you clean with a vibration table? It would seem almost impossible, for example, if you are printing a mesh or similar part.
So Helder, thank you very much for your question. The question was, do you have to physically clean with an instrument, or you can clean with a vibration table? It would seem almost impossible, for example, if you are printing a mesh or similar parts. Well, Helder, yeah, that's the question is slightly correct. So what you have seen was really how we have depowdered the parts in our material handling station. So we did this manually with manual tools because we have a semi-automatic system. And after this process, usually, if required or needed, we are using our Sintratec blasting station, which is basically a blasting station, a sand blaster, where we are putting industrial PA12 from Sintratec in that we cannot use any longer. And afterwards, if you wish, we have this fantastic Sintratec polishing station. So this is a magnetic tumbler, where actually magnetic pins are creating a smooth surface out of your part. So the peripherals that we usually recommend to have with the Sintratec starter cell are this blasting station and the Sintratec polishing station. They are both coming for a really affordable price to have a basic setup. And I hope I could have answered your question, Helder. Thank you very much for raising it. And yeah, I think therefore me and the Sintratec Switzerland team are saying goodbye today, and we hope that you are tuning in tomorrow again, and have a lovely rest of the day. Enjoy the show and stay healthy. So bye-bye, wave the hands. See you tomorrow, bye-bye.